Hi, I'm Victor, country manager of Japan Linaro. Today, we invited Tabata-san from Fujitsu, going to share the story about how Fujitsu CPU A64FX took the first place of Green500. This is the first time forever for a generic purpose CPU to top the list. And of course, Fujitsu CPU is an ARM CPU. Everybody knows ARM is the secret recipe for power efficiency. So today we're going to learn how this ARM chip, Fujitsu CPU, become the world's top energy efficient chip of all the supercomputers. Okay, Taba-san, turn to you.
Thank you for joining my keynote session. I'm Takekazu Tabata from Fujitsu. I'm in charge of instruction set architecture for Fujitsu CPU. Also, I'm interested in the core microarchitecture for achieving high performance and low power design. Today, I'm going to talk about the A64FX processor that has a power efficient design for HPC and AI. I'd like to introduce the A64FX processor. Next, I will talk about how to achieve most power efficient supercomputer of Green500. Then I'm going to talk about action for software development. Finally, I will conclude this presentation. This is today's table of contents. Firstly, I'm going to talk about the key message of this keynote. A64FX is a new Fujitsu-designed Arm processor. It is used in supercomputer Fugaku, Fujitsu PRIMEHPC FX1000 and FX700, and Cray CS500. A64FX is the first processor of the ARM VTA and SV architecture. It achieves high performance and power efficiency in HPC and AI applications. To achieve those, Fujitsu and RIKEN tightly collaborated in analyzing the tuning of these applications. Fujitsu's microarchitecture maximizes the capability of SVE. We continuously contribute to ARM ecosystem and ARM software stack with Linaro. I'm going to talk about Fujitsu processor development history. Fujitsu has been creating innovative technology for processor over generation for more than 60 years. And Fujitsu developed various types of processor, such as for mainframe, for UNIX server, for HPC. A64FX is our latest processor for HPC. And it focuses on not only HPC, but also AI. Because of those backgrounds, A64FX inherits the DNA of Fujitsu technology used in mainframe, UNIX, HPC. Through the experience of development of mainframe, Fujitsu has developed mission-critical technologies for high reliability, which contribute to system stability and data integrity. For the UNIX server, we have achieved high performance in single thread, as well as high flexibility, which can handle a wider range of applications. For HPC server, we have realized high throughput of execution and memory. In addition, we have achieved low power consumption and massive parallel system. We integrated all those technologies into A64FX. A64FX is a CPU with extremely high throughput, low power consumption, and mainframe class reliability. It is optimized for massive parallel system. Those are based on our strong microarchitecture that can be used for all our processors. I'm going to talk about a brief specification of A64FX. As an architecture feature, it conforms to standard ARM 8.2 with SVE. SVE vector lengths are supported at 500-bit, and it has a 52 core in total, consists of 48 computing core and 4 assistant core, while all cores are identical. This chip has 4 sets of HBM2 memory. The total capacity is 32 GB. Fujitsu proprietary interconnect controller called TOF-D is embedded on the chip, which realizes a 6-dimension mesh and torus network. It provides low latency and high throughput network. This chip also supports a 16-lane PCI Gen 3 as a standard I/O. The chip is fabricated using 7nm FinFET technology with a 9 billion transistor. HPC achieves a more than 2.7 teraflops peak double precision floating point performance, and it provides 1024 GB per second memory throughput. HPC uses in supercomputer Fugaku that is built by RIKEN and Fujitsu. The supercomputer Fugaku is a successor to K computer and will be used in wide range of applications. K computer used the A64FX, which developed by Fujitsu. After many accomplishments, K computer was retired in last August. Now shipping and installation of Fugaku started in the end of 2019. And HPC used in not only supercomputer Fugaku, but also commercial system. Last November, Fujitsu announced 2 models of HPC server that are used Fugaku technologies, FX1000 and FX700. Also, A64FX processor equipped in both products. This slide shows a brief specification. There are several differences between both products. Firstly, we have designed the PRIMEHPC FX1000 focusing on the 3 key factors: high performance, and high scalability, and high density. FX1000 is a supercomputer that fully utilizes technologies developed by RIKEN and Fujitsu for the supercomputer Fugaku. The scalable TOF-D interconnect can connect over 100,000 nodes, creating a ultra-large scale system. On the other hand, the FX700 has a 2U chassis that can be mounted in standard 19-inch rack and can hold up 4 blades. Each blade contains 2 nodes. That means the chassis can consist of up to 8 nodes. It is air-cooled and making it easy to deploy high-performance Arm server. The interconnect among the compute node is an industrial standard InfiniBand EDR. PRIMEHPC FX700 uses a Red Hat Enterprise Linux as OS, offering a high level of software migrability. Also, Cray and Fujitsu announced a partnership. Cray provides the HPC processor on Cray CS500 supercomputer architecture. HPC processor is attracted to many people's attention because it has a broader capability to execute HPC application and AI application. And it provides incredible high throughput and low power consumption features. Next, I'm going to talk about our effort, how to achieve extreme power efficiency with high throughput and high capability. In SC19, the Green500 November 2019 list was published. HPC Prototype won #1 on this list. That means HPC Prototype is the most power efficient supercomputer on the top 500 list. It achieved 16.8 gigaflops per watt. Compared with the second place of CPU-only system, HPC Prototype is 3 times better power efficient. The key for good gigaflops per watt is a multiply energy efficiency hardware and parallel execution efficiency. HPC designed for the energy efficient. Fujitsu program CPU microarchitecture and 7nm FinFET technology achieved it. Also, we integrated many functions on the package. For example, TOF interconnect D integrated on the die, and HBM2 memory for main memory integrated on the CPU package. To achieve the superior execution efficiency, Fujitsu tuned library using our HPC experience. We tuned, for example, we tuned the math library for the application efficiency to fit the hardware behavior. The communication library is also tuned, utilizing a long experience of TOF interconnect technology. Software tuning using the rich performance analyzer and monitor that HPC provided. Today, I'm going to talk about HPC hardware technology. Firstly, I'd like to introduce the Scalable Vector Extension. Arm and Fujitsu developed the SV, that is new generation vector extension. As our lead partner, Fujitsu contributed to it by using our HPC experience. The register structure is similar to Intel FX5112. There are 32 scalable vector registers and 16 predicate registers. The first version of the SV focuses on the HPC and AI area. Now, Arm announced the SV version 2 that focuses on the media processing and the DSP processing and another general purpose use. I believe SV becomes a standard in broader area. SV supports various data types beyond the different arithmetics. For example, to accelerate AI application, packed half-precision floating point arithmetic is supported. Also, 16-bit and 8-bit integer dot product instruction is implemented. Another interesting feature of SV has a vector length agnostic mechanism. The hardware implementer can choose the vector length, which is supported by the implementer's hardware. SV covers 128-bit to 2048-bit implementation. Also, VLA-enabled binary can execute different machines that have the different vector lengths without recompile. The meaning is SV can provide the capability for wider range of applications, and it contributes to build a software ecosystem. Let me explain the microarchitecture side. To use our processor in supercomputer Fugaku, RIKEN and Fujitsu started co-design. RIKEN has defined the 9 priority issues to have to solve. To achieve performance goals to the application, Fujitsu provided the performance estimation of those applications and performance estimation tool of our processor. Also, Fujitsu provided the characteristic of the hardware behavior. By using that information, RIKEN modified its source code to align hardware behavior and estimated the performance of the application. Based on the RIKEN evaluation, Fujitsu acquired feedback for microarchitecture design and the characteristic of the priority application. Based on that feedback, Fujitsu refined our microarchitecture design. That is, because of this, co-design efforts have made Fujitsu microarchitecture stronger and have improved the performance of application for 9 priority issues. RIKEN announced the predicated performance of Fugaku for those priority applications. Genesis and Nikam RedCave are expected to be over 100 times faster than in K computer. In addition, the geometric of 9 priority and 9 performance is expected to be over 37 times greater. I believe that it contributes to our society to solve our issue. Based on that feedback, Fujitsu implemented our microarchitecture. A64FX enhances and inherits the superior feature of the Fujitsu microarchitecture design. A core provides the 4 integer LU, 2 512-bit SIMD engine, and predicate operation unit. Also, out-of-order mechanism delivers good performance. Advanced SIMD instruction can execute on the 512-bit SIMD engine. Also, load store unit can execute 2 512-bit load or 512-bit SIMD store. To improve power consumption for the power critical situation, we developed a new technology that we have framed up then. Let me talk about the many core architecture. For many core architecture, how to connect multiple core is a critical ratio. A64FX consists of 4 CMGs. CMG stands for the core memory group. Each CMG consists of 13 core and local level 2 cache and HBM memory controller. 1 out of 13 core is assistant core. that handle non-computational operations such as a daemon process and I/O process. All CMG keep the cache coherence by CC-num architecture with a on-chip directory. The crossbar connection between the core and level 2 cache in CMG maximizes the high efficiency for the throughput of the level cache. Process binding with CMG allows a linear scalability up to 48 core. This chip uses a ring bus connection between CMG and the I/O controller, such as a TOF and PCIe. The wide ring bus secures the performance for the I/O. This diagram shows the H4FX peak throughput and byte per flow called BF ratio in HVA. By high efficient out of the mechanism in core, cache, and memory controller, H4FX can maximize the capability of each layer's bandwidth. The peak throughput of level 1 cache memory and level 2 cache memory to achieve over 230 gigabytes per second and over 115 gigabytes per second, respectively. The peak throughput delivers 256 gigabytes per second between HBM2 and level 2 cache per CMG. The BF ratio of cache and memory are very high. It means that H4FX can achieve superior efficiency for the wide range of applications. As I explained, we designed H4FX provides high performance and high bandwidth. However, generally, high performance and low power is not easy to achieve at the same time. High performance processors tend to require more transistors to implement rich control, many execution units, large cache. Also, it needs a high CPU frequency. But to lower the power consumption, we have to go to completely opposite direction. That means there are conflict demands. To get over this difficulty, H4FX realizes GPU class performance per watt, even the general HPC CPU. To handle this difficulty, we use the unification of logic and physical power design methodology. Front-end designer always considering the design goal, including the physical design and power design. The back-end designer gives the feedback to the front-end designer based on the physical design and power estimation. Improved design flow realizes quick feedback between the front-end and back-end designer. As a result of this, we could implement many ideas to reduce the power consumption, keeping the performance and bandwidth. The above figure is showing the typical ASIC design methodology. Logic designer hands off the logic and physical designer press and route and feedback to logic designer. Try to design waste design time and make unnecessary design margin and waste performance, power, and area. By using our methodology, logic designers and physical designers were working together. On front-end side, logic designer implemented specification design considering the power consumption. On the back-end side, physical designer gave the feedback every day and optimized the performance power area. It minimizes the design margin and better performance power area. Daily improvement achieves such kind of good power consumption and create new idea to improve the design for both parties. As a result of those methodology, we achieved high performance, high bandwidth, and high performance per watt. Actually, I'd like to show the benchmark. We have evaluated the performance for 7 popular OSS applications. This graph is a relative speed up ratio compared with the 2 CPU of x86 processor and a 1 CPU of the A64FX. A64FX is up to 1.8 times faster over 2 CPUs of x86 processor. High memory bandwidth and long CMD lengths will work effectively with this application. I'd like to show another result. We also achieve the high, we can obtain the up to 3.7 times more efficient over 2 CPU of x86 processor. for the power consumption. Those results come from doing both high performance and high performance power to design at the same time on the H4FX processor. Next, I'd like to explain action for the software development. Firstly, I'm going to talk about the Fugaku. Now, RIKEN and Fujitsu are developing software stack for supercomputer Fugaku.
Tabata-san, can you hear
This
me?
compiler are optimized for our microarchitecture and maximizing SV and HBM2 performance. We collaboratively work with RIKEN, Linaro, OpenHPC, OSS community, and ISVs. We continue to contribute to the Arm HPC ecosystem through the supercomputer Fugaku. Another action is RIKEN and Fujitsu verify the SPACs over 3,000 recipes for multiple compilers. So SPACs is a flexible package manager for HPC software. Now, if you're interested in, please check with their website. For AI, H4FX has a binary compatibility with other ARM systems. Therefore, user can use ARM open source AI software stack. Now Fujitsu is porting a tuning and DNL library for H4FX and SVE. We will disclose those accomplishments. Fujitsu continues to contribute through the porting and optimizing the software stack for ARM architecture.
Hi, Tabata.
Finally,
okay.
I'm going to conclude. H4FX integrates Fujitsu proven microarchitecture with the ARM ISA and Fujitsu for design. H4FX is the first processor with ARM V8 and SV architecture. It is used for Fugaku, Fujitsu PRIMEHPC server, and Cray CS500. Fujitsu collaboratively work with a partner and continuously contribute to ARM ecosystem and ARM software stack with Linaro. Thank you for your attention.